So here are the new problems for the week. The first homework, 5-HW number 1, we see listed here on Blackboard. It says, in working with a company, you find that they have averaged 65% power factor over the past year. They are on a rate schedule that's shown in figure 3-10 of the text, and they've averaged 1,000 kilowatts per month. Neglecting the ratchet clause and assuming that the demand and the power factor is constant each month, we want to calculate the savings for correcting to the 80% power factor the rate asks for. How much capacitance in kVARs, that's volts, amps, reactive, would be necessary to obtain this correction? Assume that they are in transmission service PLY, which is level 1. My assignment for you is to use the solutions provided in the solutions manual listed above here in Blackboard to create an Excel file that performs the required calculations. I want you to email me that file. The files for this week can all be combined into one single worksheet with individual tabs for each assignment. The assignment is due on February 22nd at 11:59 p.m. next Monday night. So, I didn't cover power factor very well in my PowerPoint last week. Many of you have had DC-AC circuits already, and power factor was discussed later in the term of that class, but perhaps not always very thoroughly by the instructors. So what power factor is, it's a ratio of true power measured in kilowatts to reactive power measured in kilovolt amps. If the ratio is greater than 80% or 0.8, the utility companies can and may charge a penalty imposed on all purchased energy. So it boils down to the utility having to generate, in this case, our problem of 1,231 volt amps in order to sell 1,000 watts of energy. They really do have to use more fuel to do this. So we have to calculate the size of the capacitor that will offset the inductive reactance caused by motors and wiring in a facility. If we wanted to correct to 100% power balance, as shown here, we would have to reach a 1169 kVAR amount of capacitance. Well, we don't. We only have to get to 80%. So instead, we calculate to come up with not only the 65% power factor, which is 1169 kVARs, but also the 80% power factor, which is 750 kVARs. So when we subtract one from the other, that's where we come up with this 419 kVARs. So there is a power factor correction table that can be found in many places. One of those places would be the Uglies book. I'm going to show you that here. I happen to have a digital copy of it. The Uglies Electrical References Manual, that's what the cover looks like. And when I come down to calculate, and this is the table of contents for capacitance, right? It's going to show me how I can calculate capacitance. And as I keep going down, it'll do the capacitor color code, and those are starter caps. Now here's power factor correction, right? So again, it told me that on the page before. This is the table values times the kilowatts of capacitors needed to correct an existing desired power factor. All right, so if the existing power factor was 65 and we needed to bring it to 80, then we just come across here, 65 to 80. Notice they come up with 418. Our calculations were 419. Close enough. We multiply that times the number of by what the load is. All right, and then they give us a really nice problem in order to solve. Now, I'm not asking you guys to look at this. You may not have an Uglies book, but if you do, this is a good way for you to really finally understand how this power factor works and how it's calculated. It works out really well. And if you'd like, and you have a copy of the Uglies book, and you'd like to include this in an Excel spreadsheet, I'll be glad to give you some extra credit if you can show that it works out. So that's using the Uglies book. I also found a really nice example of a tool on the internet, and this was a power factor table calculator made available by Schneider Electric. Schneider Electric is the company that bought Square D. So they've been doing electricity for a long time. So notice the search window. I searched using Excel to calculate power factor. Some of the things that popped up didn't work, right? But this top one did. And if I were to click that, what happens is an Excel spreadsheet downloads to my computer, and then that download can be run, and it works very well. Let me show you that. So back on Excel, this is the window that's going to pop up. This is the power factor table right here. So look at this. So this is what we'll use for selecting the capacitor size. Now, notice the nice thing about it. I have selected the kilowatt factor here I've selected that window, and notice up here in the formula box it gives me exactly how to enter that information in. I have to take the tangent of the arc cosine of the 65%, right? And that has to be subtracted from the tangent of the arc cosine of the 80%. Now all that's showing, we see K25, that's this block here. This is K25, right? So K25 is the 80% that I plugged in. The 65% I plugged in here in K23. I can literally plug that right in here. And if I tell it what size load that I have, it tells me exactly what I need here. So it really works out well. The thing I like most about this is it gives me the formula, and it helps me to learn how to apply these functions in Excel. So great little tool. And again, I found that by going to this website right here. I typed in using Excel to calculate the power factor, and it showed me power factor table calculator. And when you click on that, it will take you to that sheet. Let's go back then and look at the solutions guide, and sure enough, it shows us the same things. All right. The next problem is 3.5. 3.5 right here. A company has contacted you regarding their rate schedule. They are on schedule, the schedule shown in 3-10, which is a service level 5 secondary service, but they are near transmission lines, so they can accept service at a higher level, meaning a higher level voltage, if they buy their own transformers. Let's assume that they're consuming 300,000 kilowatt hours per month, and that they're billed for 1,000 kilowatts of demand each month. How much would they save by owning their own transformers? Now we're going to ignore any charges other than the demand and the energy. So we're going to use the solutions provided here, right here. When we go down, we're going to see, it shows me exactly how to do it, but what are some of the assumptions that it makes? Okay, here's one of the assumptions. First thing we have to notice is that we use 300,000 kilowatt hours per month right here. So that 300,000 kilowatt hours per month means we'll never use this lower rate of less than 3 cents per kilowatt hour. We're never going to use that. So the only rate we're going to use is here. Nice. Okay, so we're going to do a spreadsheet that's going to compare the two different rates. Those two different rates will show up here, and they literally take you through, and you be able to use Excel to come up with these same answers. That's the challenge. Use Excel to come up with the same answers. All right. Shouldn't be a problem. Again, that's your job. Just put it together and send it to me. Notice that they're going to save $30,000 a year. Is that worth it to own our own transformers? Well, I guess we'll have to figure out how much transformers cost. Do we have the space? Will that add to our heating load? There's a few questions that we'd have to ask about that. So that's 3-5. All right, back on the blackboard. Homework number 3. Homework number 3. This is the first problem where we're going to deal with gas billing. So, in working with a brick manufacturer, you find gas billing that they were placed on an industrial priority 3 schedule, and that's listed on figure 3-12. The business and inventories are such that they could switch to priority 4 schedule without many problems. And inventories, business and inventory. So it must mean that priority 4 allows them to have their gas service interrupted. So what would the savings be if they switched from one rate to the other? They consume 7,000 MCF. Now remember, MCF stands for 1,000 cubic feet. So 7,000 cubic feet of gas is 7 million cubic feet of gas per month for process needs and essentially none for heating. So again, we're going to give you the answers, and you're going to create a spreadsheet that's going to work it out for you. So let's take a look at this the answers that were here. All right. Notice this present rate scale. And I want to point out that these first few lines right here, these first few lines, right, 1, 2, 3, 4, 5 lines, those lines are for the first 200,000 cubic feet of gas, right? Now, that's all that is. And then once I get over that first 200,000, right, then we add up to the next 7,800,000 cubic feet of gas. Now, if you're a little confused about this MCF stuff, go back to page 9 of your text, and you can read up again on how those rates worked. So notice also that we use 7,000, but notice this rates ends at 7,800. So we're never going to use this bottom line. We'll have to calculate the first 100 cubic feet, the next 2,900 cubic feet, and then so on and so forth. And they're actually showing us here. So you have to set the spreadsheet up to do this work. Notice they show the monthly cost here, and they don't show you that you have to multiply that times 12 months. Your spreadsheet will have to do that for you. And then we're going to do the same thing. We'll calculate the same amount of energy rate using this priority 4. So last, I want to make sure you think about what if. So there exists a 20% possibility that switching to the proposed rate schedule will disrupt production 1 or more times a year for an hour. Will that 1 hour of loss of production make it worth saving the nearly $24,000 annually? Question that the management has to answer, and we as the energy managers have to make a case for whether we think it's a good idea or not. All right, couple left here. Let's go back to the blackboard and look at question number, homework number 5. Week 5, homework number 4. In Chapter 3, Problem 3.7, we need to calculate an electric bill for a customer with a January consumption of 140,000 kilowatt hours, a peak 15-minute demand during January of 500 kilowatts, the power factor of 80%, and an electrical schedule of shown as in the example in 3.6. All right, which by the way, that is found on page 122 of the text. And we're going to assume that the fuel adjustment rate is 1 cent per kilowatt hour. All right, again, everything's due next Monday. Let's take a look at the solutions manual for this guy. Here it is. We're going to look at a bill. This is it's pretty simple here. So this is the information that we'd find on page 122 of the text. This is that figure 3-6, right? And notice, plug all the math in. The only thing I would really like to point out here is how you enter the percent of taxes. Okay, you can enter it as 8, or you can enter it as 0.08. It all just depends upon how you will use the equation inside Excel. Last thing is I also want to point out here that sometimes that fuel adjustment charges, as shown here, are not taxed. Okay, so in this case, we're adding it up to the subtotal, and that $1,400 is subject to tax. There might be cases where that isn't the case. All right, one left. Homework number 5. Homework number 5. Problem 3.8, we're going to compare the following residential time of use electric rate with that shown in figure 3-6. I'm sorry, that's the one. And that's on page 98 of the text. Okay, this rate charges less for electricity during off-peak hours, which amounts to about 80% of the hours in a year, than it does for electricity used in the on-peak hours, which would be in the other 20%. So the question he's really asking, it states compare the following rates, but it never asks the question. Okay, I looked at them. Here's the question. What is the average cost per kilowatt hour for each rate? That's what we want you to find out. Now let's look at the solutions manual. There's something I need to show you on this one. Okay, and on this one here, notice it shows me the rate, this new rate we're thinking about using compared to the one that's on page 98, figure 3-6. Okay. One thing we'll notice right away is that the dates and times for each rate aren't the same. We're not comparing apples to apples, so it's slightly different, which may make it difficult for the customer to decide whether or not they can adapt to these new hours. Yes, these new rates are lower, but what if they can't adapt their lifestyle to using the electricity during the off-peak hours predominantly? So that's what we're looking for. I do need to point out that there's a typo in this book, right? Notice right here, very important, this is a typo, okay? So when I compare this rate for electrical use during off-peak time, there's an extra 0 in here. And because there's an extra 0 here, there's an extra 0 in the answer, right? So this bottom answer right here, this is really important. You have to change that. You have to pull the 0 out here, so it's 0.058, and it results in it results in an error. So this answer shown here in the bottom is incorrect, right? It's incorrect. By changing this number up here, right here, you guys should be able to determine what that new one is. So there's a little bit of a challenge for you. I'm not going to give you all the answers right out of the gate. All right. That's all we got for this week.